time independent part. It is high grade. So this is what we were after, and we wrote down this operator as the today's class will be heavy in calculation, but very systematic step-by-step calculation, almost like an algorithm. Very simple calculation, but longer and conceptually very simple. It's just repetition of what we learned. R squared is theta. Okay, so this was the form, and then what we did, we used an identity to show. We used this identity. This is nothing but a definition, but this is an identity. This is what I'm going to write. R squared P squared minus R dot P squared plus P dot R dot P. Now using this relation, we wrote down the P squared as, because this del square is nothing but minus h square by 2 square. Actually, minus h square by this. Del square is p square, not 2, and p square is therefore 1 by r square del square plus p square p. And then if this is true, we can write this r dot p as r del r, because this actually minus I over r del r, because p has all these components, but r dot means it's only projected on the r direction, so only the r component of p, and then I going to put everything together. It becomes minus 1 by r square r dot p square. So this quantity these things I already wrote down before, so don't need to copy it, just warming up for you to get easy for a Monday morning class. This is a repetition of what we did. So this is just expressing this. This is after t. I will subtract this, expand this, and write it in a short form. Just take that, and that means the p square becomes this quantity, h square by r square del r square del r plus this quantity del square by r square. This is a useful identity. That means the p can be written as a r dependent part plus a theta phi and r dependent part, which is a whole constant L. Now it's L. We can see that it is L, but why it is a constant that is not apparent from here, but that is something we discussed separately. We discussed earlier that this problem has rotational symmetry about x, y, z axis. So it has the coordinate x, y, and z. If I write it in Cartesian basis, that means there is a px, py, pz as conserved because of transition symmetry. But because of this rotational symmetry, there is a Lx, Ly, and Lz also conserved. and this Lx, Ly, and Lz, they must, all of them must commute with the Hamiltonian. And then trivially there must be a quantity also L square, which is L square plus Ly square plus Lz square. That is also the total angular momentum.
Sir,
Yes.
sir, your voice is thoda echoing. It feels like their mic is like your mic is not working or something.
Hello. Can you hear me clearly now?
It's same, sir. It's like it feels like your voice is coming from after echoing from the room only.
Once asked them, sir.
Hello. Huh?
Once asked them. And now?
Now? Can you hear me clearly now?
No, sir, it's same. The other person who said just now, his voice is pretty clear.
What other person means?
Oh, I think my voice is clear, he's saying like.
Your voice is clear. What is happening?
No.
Hello? Hello? Yeah, the machine shows true. Is it true for everybody or for only some people? Is my voice?
It's also same issue with
Sir,
me.
I can understand, but something is like.
Sir, when you are just speaking near the device, then it's clear.
Can you call a IT person?
Yes.
Okay, so IT person is coming and check that. Let's continue meanwhile. Okay, so we further understood. Now this part is very unusual compared to all other problems. Is that each commute with L square along with each commute with Lx, each commute with Ly, and each commute with Lz.
Hello.
All of them.
number 330.
But they don't mutually commute.
Huh?
Um,
Sir, room number 3305. What's the problem?
What was this thing? IH bar, maybe Civita IJK, LK, right? This one doesn't come. And this is not this is not a just a artifact of this problem. It is generally true because what is Lx, Ly, and Lz? They are generator of rotation in X and Y and Z. And we know they don't come. Right? This is general property of it. So for example, look at this sheet of paper. So if this is my Z axis and this is my X axis, so if I rotate it by some angle by Z axis, and then I rotate it by some angle by X axis, it will become this. Right? But instead of that, if I rotate it first by X axis and then by Z axis, it becomes this. Right? Two completely different orientation. If I look at this like this, this is my sheet of paper, this is Z, this X, this Y. So if I rotate it first by Z axis, it becomes this. Right? Let's say 90-degree rotation. Then if I rotate it by X axis, it becomes this. So your final orientation, you started with this orientation. And you did up. So let's say X, Y, and Z. You first do a Z rotation by pi by 2. Z at pi by 2. You end up here. You become this. Then you do it. X and Y by 2. Then it becomes. This is the final orientation of this piece of paper I told you. But if you first do X and pi by 2, it becomes this. Then if you do Z at pi by 2, or then Oh, okay. Now let's do first X and Y1. H to make it. I will draw it wrong. Let's let it. X, Y, and Z. So I do first X rotation, it becomes something like this. Yeah. Now if I do a Z rotation, it will just become that. That is this step. This X step. So you can see if I do first Z rotation, then X rotation, and if I do first X rotation, then Z rotation, I get different something. So this fact that two generators of rotation doesn't come in is a representation of that fact. Very easy to remember. But interestingly, yeah, can you hear me now? They were funny. They did fix something.
Yeah, sir, it's fine. It's
Sorry?
fine.
It's fine, right? Okay, very good. So then we show that there is another L-square operator which commutes with all I, not all I, and it commutes with basically everyone. It commutes with also this. So L-square commute with everyone. Lx, Ly, Lz commute with H, but Lx, Ly, Lz mutually don't commute. So this is, I just presented it as a, so you can, as I said, that you can just check by so that what was Lx? Lx was what is Z. So I told you can check, just check this as a by looking at the properties of this. But there is a deeper structure into it, which we will learn next week probably. Is that so? This L square is this whole thing. As we know that these they are satisfying some Lie algebra Lie group, and this L square is called the Casimir of the group. It's a Casimir operator. Now, what is Casimir? Just a name, but it has a deeper meaning that it's an operator that commutes with everything. So if you write it actually, this L square operator form is actually some number times an identity. So it's when you go to the matrix representation of them, they are basically a identity matrix. Of course, identity commute with everyone, and we'll see that there are very interesting consequences for existence of such a L square operator. But for now, let's just proceed with the structure and mainly with the calculus part of solving this problem. Then we'll come to the algebraic part, which gives you much more deeper insight. So, as you know, one problem we solve in two ways. One is algebraic way, and then is the calculus way. So, we are now focusing on the calculus. Okay, but for now, just notice that this structure is there. But most importantly, you remind yourself, as you know that already we have spent a lot of time doing this. When you have many, so you have that many conserved quantity. Okay, this should be completely able to specify your Hamiltonian, but we have more than what we need because we know there are 3 degrees of freedom in this problem, that is x, y, and z. If we go to some other coordinate, it becomes r, theta, and phi. But we have 5 conserved quantity, but not all of them are independent. So you can choose 3 of them. If there are 3 degrees of freedom, you need 3 numbers to completely specify nx, ny, nz if you are in Cartesian. So they are, these 3 numbers are, it's an ad hoc choice. You could have chosen something else also out of Lx, Ly, and Lz, and they forms a CSCO because of this mutual commuting structure. Okay. So this is what we learned last time. That's so far so good, all revision. Okay. So now let's even if you are lost in the details of the algebra, this much, this box equation, these relations and this form and this idea, you must be always there. From now onwards, it should be permanently there in your mind. Okay? If you understood it. Okay, you might forget the details, but this much should be there from now. Okay, now I wanted to solve this now I start to move towards solving this the eigenvalue equation of each of these operator. So we started with L square. So noted that L square and Lz, so they must have a common eigenvalue, and we referred that common eigenvalue as okay. I referred, since they have a common eigenbasis or common eigen, sorry, I used a wrong word. I said they must have a common eigenvalue. That's not true. They must have a common eigenstate, which, and that could be, you should be able to label it by their eigenvalue. So this eigenvalue is Lm. So L for L square and M for Mz, Lz. So this is just a convention. You could have chosen anything else, but L stands for L square and M stands for Lz. And if I choose that, so I should be able to write a eigenvalue equation. The h bar is for matching the dimension because the Lz has a h bar in it, and L square YLM. It should be L h bar square by Lm. But I asked you to think, and I hope you thought about this. That why instead of this I am writing, there is no loss of generality by writing it like that, but why such a peculiar choice? So it will give you, if you know this, tell me. If you don't know, tell me in the next class, in physical class. But knowing you, I think you have not looked into it, so probably you don't know yet. Okay, so now I want to solve each of these equation. I have not done anything new so far. I am just revising the last class. So if you want to solve, the first part is particularly easy because Lz is nothing but minus IH bar del phi. So this equation is nothing but minus IH bar del phi YLM MH bar YLM, whose solution is, so YLM have a theta and phi part. Okay. Let me refer the theta part as PL cos theta. This is completely an arbitrary choice why I call it PL cos theta, but I'll show you in a moment that there is a particular reason for that. And the phi part is, this is the phi part. This will be definitely Im phi. And the compactification that tells you YLM theta phi plus 2 pi is equal to YLM theta phi. That guarantees M must be an integer. It must be an integer 0, 1, 2, 3. So this much we have discussed already last time. So everybody, so far, in first half an hour of the class, I am just revising what we discussed last time. If there is a question, clarify it right now. Okay, very good. Good to hear that. Good to see that you all totally understand everything. Okay. So now I want to solve the other part, which is more difficult, the L square part. Difficult means it's just complicated, it's not difficult. So let's now write down the L square part. So this was for the Lz part. Now the L square part. So L square part will give me, we have to find this kind of problem we did earlier also. We have to find the full eigenstate, that is eigenstate of both Lz and L square. So this is the only phi part we found. This is not a eigenstate of L square yet. So we have to find the eigenstate of the L square. So L square is h cut square 1 by s theta del theta s theta del theta plus 1 by s theta square del phi square YLM theta phi is equal to h cut square L into L plus 1 YLM theta phi. So we have to solve this equation. This equation looks a little intimidating because it looks like, okay, it's not only a partial differential equation, plus it has this weird combination of theta and phi on the left hand side. But fortunately, you can clean up this, and this looks very nice once you clean up. So the cleanup is following. You plug in the form of YLM, which we wrote down here, and that YLM form is actually, I should also have a M index here.
Sir, is that PLM of theta? Sir,
Sorry?
is that PLM of theta where you just now put M?
Ah, yeah, in this part.
Yes.
Correct. Very good. So, very good to see that you are alert. Okay. So, this is my ansaj or trial solution, because the 5 part I already figured out, P I didn't. There is nothing actually trial. It is just a natural form. So, now I plug this into this. Okay. When I do, after some algebra, so let me write down one more step of algebra. So I just plug in. So I plug in means it will become e to the y m phi l theta. Nothing changes in the phi part. Phi just comes out, and PLM theta is the only thing to be taken derivative of. Del phi square, you only work on the phi part. So you take twice derivative, it becomes m square in front. So when you do this algebra, you get following. This is nothing but s theta del theta, s theta del theta. So what I did, s theta I multiplied, I multiplied it here and here, so it becomes s theta square. So s theta square by s theta is just s theta minus m square s theta del theta. Okay, very simple algebra. Did I make something? No, it's all right. Okay, so h bar square from both sides cancel. S theta square I take upside, so this becomes s theta. This just becomes m square because I took 2 derivative in phi, and this becomes just l into l plus 1 times m square. Okay, so that's the minus I have taken from this side to that side. So now I will do a little more massaging, and this equation will become very simple after that. So let's do that here, right next to it. Okay, so this equation, let me write one more step here. Then I go to the algebraic form. So s theta del theta s theta del theta PLM theta, and then I take this in this side, just rewrite it again. It becomes L into L plus 1 s theta square minus m square PLM theta equal to 0. Okay, I did nothing. I just rearranged this. I just took this term on the left side and just wrote everything together, just for simplicity. So now I will do something really useful. So I will do a variable transformation and write cos theta as x. Okay? If I do that, then your del theta will become minus s theta del x, because cos theta's derivative is minus s theta, and your s theta del theta will become minus 1 minus x square del x. This is easy to see because if del theta is s theta del x, s theta del theta is s theta squared del x, and s theta is 1 minus s theta squared is 1 minus c theta square. Sin square plus cos square is 1. So that's why, and since c theta is x, so I can just write this. Okay. So now I plug this whole thing. I plug this whole thing into this rearranged equation, and then this becomes a nice algebraic equation. It becomes it becomes 1 minus x squared. So don't worry, I'll give you all these notes, but just understand what I'm doing, the outline. Outline is very simple. One minus x square del x PLM. Now everything should be written as a function of x because I write cos theta as x. So theta is some function of x, complicated function, plus L into L plus 1. Then I write this term s theta square. So s theta square means 1 minus x square. Since s theta is 1 minus cos square theta. This is what it becomes. This whole equation becomes a algebraic equation. Now, what's the advantage of doing that? This is actually a familiar equation. Sorry? Where? Can you say loudly? Yeah. S theta del theta. Yeah, 2 minus give you plus, right? Okay. Okay, good. So now this equation, I will write it in a little cleaned up form, which might make you familiar that where you have seen it. And this is usually taught very often as a typical example. So let me just write it in that form. So del x. So now I put it in this together, and it becomes 1 minus x square del x PLM x plus L into L plus 1 minus m square by 1 minus x square. What did I do? I just divided by 1 by x square. Okay. If I divide it, this del x part looks a little more clean. This become L into L plus 1. This 1 by x square is down, so this cuts up, and this remains like that. Okay. So this form is called a Legure differential equation, and you can get the solution exactly like before, the series solution, and the series form gives you something called, no, not Legure, this is not Legure, sorry, this is Legender. This is the one which you learn always at the first example. I can't keep remembering those names. This is, you might think, who the hell solved those kind of things? This is a French mathematicians. They are all Legender, and they are all French mathematicians. And they solved it because they are not just exclusive to quantum mechanics, of course. They come also for the spherical wave equation and all that. So this solution, so this is a series solution you can do, which you probably
Sir,
either going to do or will, yeah.
sir, can you write a little bit bigger?
Okay, yeah, sure. So then what the solution you will get if you solve it is PLMX these sorry, not PLX. So if you get the PLMX by solving this, or this is the M dependent part becomes this, and this is the PLX, and the PLX is given by just written in this convenient form, and when you do series solution, these forms just come out. So just notice what is happening here. PLX is the Lth order derivative of a Lth polynomial, and PLMX is again similarly the mth order derivative of this PL polynomial. Okay, so yeah, I will just give a sketch of how to solve this actually, but you should try it yourself, not do it in the class, because it's cumbersome and not very cumbersome, but we have already done. I mean, there is no point of learning gravity for apples and oranges separately. So I will just give you an outline that how to solve this kind of equation, which you already did. Is this just series solution? So let's say I want to, for simplicity, let's take the m equal to 0 case. What happens in the m equal to 0 case? This term drops up. Okay, so m equal to 0 then will become del x 1 minus x square del x PLX. M equal to 0, so I just write it as PLX. L into L plus 1 PLX. So this thing is called, well known as Legendre equation. When you have the same also, this is called associated Legendre. So this is associated. This is a complicated additional term. So this is just Legendre. So you can now have a polynomial solution like this, where you say PLX is nothing but a k x to the power k equal to 0 to infinity. Then you plug it in. Of course, infinity or not, that you don't know a priori, but you will see the same stopping condition and everything. So you plug that into this, you get a recurrence relation which looks like this. You get a odd even solution just like before, minus n into L plus 1 minus k to k plus 1 divided by k plus 1, k plus 2, and so on. So this you want this series also to terminate, must terminate if your x is plus minus 1. Why? Because in one side you will see this 1 by x square was divided there. So if the series is not a terminating solution, then you have some divergences. So this will give you the stopping condition, and you will have the allowed L's are all 0, 1, 2, 3, and so on. Also, you notice that you have when you look at the full solution, so let me just write down the form of these solutions. So the P0 is 1, this polynomial expansion. P1 is x, P2 is half 3x square by 1. Although it looks intimidating, it is not that bad. When you expand this, this is what you get. And P3 is and so on. So this is just a, if you draw, this is just a line, this is just a straight line, and this is just a parabola, and this is a second order polynomial, and so on. This is how the number of nodes and etc. all that you want, that is all normal and consistent. And one more thing you must notice, that from these two pair of equation, that if m mod is greater than L, then PLM is 0. Why? Because this implies taking mth order derivative on this polynomial. So if you take the number of derivatives is higher than the polynomial order, then it will be obviously 0. So that you naturally get from this series solution condition. But that gives you a constant. I told you earlier that L could be 0, 1, 2, 3 and so on. But m must be less equal to L, because otherwise the function vanishes. So m must be minus L, mod m must be L. So minus L to minus L plus 1 to L. It must go up to L. So within this range, it can go from minus L to plus L, such that the mod m is at least equal to L. It cannot be bigger than L. So these two, in order the wave function to be non-zero. Okay. So this is all you need to know about this. One more thing you need to know is how to. So this YLM, of course, it is not a normalized function yet. So let's see how to normalize it. So when you normalize it, it becomes this. So you want it to satisfy okay, it's spherical, so it is sine theta d theta d phi, where theta goes from 0 to pi and phi goes from 0 to 2 pi. This must be equal to delta LL prime delta MM prime. So this is the orthonormalization condition, and physically speaking, it will come because this is a we want this to form a basis. That means we want it to be orthonormal. But this is also known that this Legendre polynomials forms a orthonormal condition. So when I put this in, if I put these functions, whatever we have worked out, this Legendre form, it turns out the orthonormalization you get is following. So ILM. This is again a cumbersome calculation which I will not do. 2L plus 1 by 4 pi L minus m factorial L plus m factorial minus 1 to the power m e to the power im phi p L m theta. So this is the full form of YLM theta phi. Satisfying this orthonormal condition. So these things are called spherical harmonics, because they form a harmonic basis for this spherically symmetric problem without any r part, only the theta phi part. And this L, there is a name for it because of historical reason. The L is called the azimuthal quantum number. We will see that how it connects with the azimuthal quantum number, which you might have learned in chemistry or elsewhere. And M is called magnetic quantum number. So this is the full solution. That is a common eigen function of L square and Lz. When you apply Lz on it, you get mh bar as an eigenvalue. when you apply L square, you get L into L plus 1 H cut square. So this is the way to get it. It's a bit cumbersome, but it's very straightforward. And this solution is the spherical harmonic solution. Okay, any questions up to this much? There must be something, right? Because this is not a something easy to digest in one lecture or one hearing. It might be easy if you are following very keenly, but if your concentration is broken even for 10 seconds, then it's very hard to follow. Not 10 seconds, 30 seconds, let's say. So, did you follow
Sir,
the outline, or I need to repeat something?
sir,
Yeah.
the part where you have written the form of PLM of x as
Uh,
1 minus x square to the power of mod m by 2 d by dx.
this term?
Yes, sir. Yes, sir. Like
Yes.
how
Tell
is
me.
that coming? How is that coming?
So how is that coming is complicated. That's why I didn't get into that. The how is that coming
Okay.
is this. That if I know this solution, so let me say that once more. So this is my full equation, right? So did you
Yes.
understand this solution, the
Yes, sir.
outline of this solution?
Yes, sir.
Okay. So it turns out that if I take this solution, so this is the PL. Okay. Now now this equation differs from this equation by the presence of that m term, right? So if I add the m term and use the structure of PL and again do a series solution, then I get this m. Okay, this m form. So this is
Okay.
the way to get it, but again, if I don't want to do that in a class. It's a very complicated form. Not very complicated, just a bunch of steps of series solution.
Okay, sir.
Okay. So there is a handbook called grad style. So normally what we do, grad style. Nowadays we don't remember how to solve all these things. So what we do, this book has a list of all such equation known to mankind. Okay, and all such integrals and all such equation known to mankind. Gratstein and Rezik or something. The second author I don't remember. And whenever we encounter an equation of this kind, but not like this, of course we know this one. We open that book and see the solution there. Okay, because solving it is a thankfully that physics and mathematics are team games. Someone have taken the pen and did that solution, and we are using it. Okay. Okay, very good. At least if, read it up once. You don't need to do it by hand and understand the structure of the solution. It's not very important for you to actually do it, but if you do it, it will gain some confidence that how to do. Actually, legendary one you probably either will do it or already have done in mathematical physics. Did you do it in mathematical
Legendary equations,
physics?
we are doing that.
Oh, you did
Legendary.
legendary. Oh, very good, very good. So then you know already. Okay, very good. So I was just feeling that, oh, should I do it or not? But then now that you have done it, it's good. Okay. Okay. So now let's. So we have now only solved the theta phi part. Now the R part. Now the good news is this part is not that hard. So let's wipe up the board, assuming there is no problem. If problem, ask me what are the issues. Now I'll go to the solving the R part. So there is an interesting discussion I could had if there is some time, but I just triggered the thought to you and ask you to read it. There is a notion called integrable system. So integrable system means it has nothing to do with quantum mechanics. It is a classical statement. So, but quantum mechanics has interesting aspects for it. So if a system has number of conserved quantities that is equal to or more than the number of degrees of freedom, those systems are called integrable systems. Why? Because that means it has integrals of motion which is more than or at least equal to number of degree of freedom. So you can completely specify the system in terms of the integrable or the integrals of motion. Okay. So when that happens, then the solution becomes particularly simple. They are exactly solvable problems. This is an example of that. But many problems that are of interest of our time especially, there it doesn't happen. So there is no integral of motion, or there is number of conserved quantities is much less than the usually energy is always conserved. That is also not always true if it is an open system. So then there is not much conserved quantity. So then it's very difficult to solve those problems. Often we just do numerics. But turns out some system has a hidden conserved quantity. So that is a very interesting topic nowadays. So what there is a field of area work called many body localization, where people discovered that some people, some systems doesn't have. Again, this is going a little beyond what you know already. Doesn't thermalize. Doesn't thermalize means they are non-ergodic. So usually integrable systems are non-ergodic. So because they are confined. They are confined in a, they have so many conserved quantities, so many constants, they are confined in a subsection of the Hilbert space or phase space. But these systems doesn't have a conserved quantity, yet they are confined. So then there are people found they have some hidden conserved quantity. They are called local integral of motion, and that is very interesting. Okay, so just know this idea of integrable system. The integrable system and non-integrable system. It's a classical notion. Just to Google it and look it up a little bit. I will not go in that discussion because it becomes a very a little advanced topic, not very advanced, and it will derail from the proposed syllabus. So I will try to follow the syllabus that we promised and have this discussion elsewhere. So exact solvability is a very interesting question. So there is a book by Baxter called Exactly Solvable Models. So look it up, it's very interesting. So one of the reason that this guy, you know, this Deepak Dhar owned this Boltzmann medal, because he came up with an exactly solvable model of this sand pile, which is a self-organized criticality problem. Anyways, so let's get back to the original what we are doing. So what we are doing is this: we wanted to find a solution of this problem, and we said this is given by okay. So we found the solution of this part. We found the full functional form of that what satisfies this, which is this YLM, but that doesn't fully solve the problem yet, because this is solution of this part, but the full equation has a R part also. Okay. So now we want to see that how can we do to solve that problem. So I can write this psi E L M as R. So there is his energy eigenvalue, that's why I'm writing it as E. So R Y L M theta phi. So this is separation of variable. The separation of variable says the theta phi part and R part should be separable, and the theta phi part is not separable. That's why we had to go through. Actually, theta phi part is also separable. No, theta phi part is also separable actually. So because it's I phi times whatever it is. So that part we already solved. So now I want to know that if I plug this into this equation with this form, then what is my solution of the R part? How the R part will look like? So we can do that. So there I used a simple identity actually. Uh, so identity is this. So show that 1 by r square del r square del r acting on r y, right, plus b r y e r y, right. If I plug this r and y into this equation, then this is how it looks like. Okay. Now do this exercise and show that. Now y I can take out because y is theta phi dependent. So let me get rid of the y. Y I don't need. Okay. Now this thing is same as I am missing something. H cut square. Yeah, I'm missing minus h cut square by 12. Now this thing is same as 1 by r del 2 del r2 r times r. So show that this thing is same as this. Just do 2 lines of calculus and show that. And this is minus h cut square by 12 plus vr equal to er. Okay. Okay. So that means I can, no, I have some missing terms. I have missing terms is this. There is a the missing term is L square by 2m r square. I miss this term. This term. Okay. So this is L square by 2m r square. Okay. So now I can rewrite this equation as okay. Just cleaning up the equation a little bit. Now I can switch to a different notation called u is equal to rr. So this rr I am just calling it a u and rewrite this equation in the form minus h cut square by 2m del r square u plus vr plus l into so this is the equation I have to solve now. So try to follow this, try to show that nothing I have done nothing actually. I just writing this equation and I use this substitution that rr is equal to u. Then I got a differential equation for u. And my final solution then of the form psi e l m r theta phi. There is a r part. R is u by r now. U by r y ln theta phi with some normalization. Okay. This would be the solution of the full problem. I have to solve this differential equation to get the solution of the u part. And this thing you can think as some effective potential, which has the regular potential plus a 1 by r square term. Okay. Now notice my 3D equation now boils down to a 1D equation. This is r, where r goes from 0 to infinity. So it's a 1D equation in the half line, not minus infinity to plus infinity plus half line. So that is the beauty of this whole structure, that I started with a complicated 3D spherical coordinate problem. Using the symmetry of the problem, I got rid of the YLM part So the theta phi part has no VR, nothing. It's generally true for all problems which has that structure. So the potential is only in the R part, and the R part looks like this, which I can think it is another 1D differential equation because it's like 1D with the effective potential of this form. Okay. So now my job is to just solve this 1D equation in half line. That is what we will do in the next class, and that's where I stop today. So if there is a question, you can ask here, and else we will meet. Tomorrow is holiday, I think, so we'll meet on Wednesday. Yeah, let's see if are there any student? A few students are there. Yeah, so you can see the point of this. Even if you have not followed all the small details, at least see the point of this exercise. The point of this exercise is that I started with a problem which has this kind of a spherical symmetry. Spherical symmetry, which means the theta phi doesn't matter, only the R matters. So therefore, I should be able to solve the theta phi part without any reference to the potential. That's what we did. So that is the thing of separation of variable. The theta phi part we solved, and because V is only a function of R, and theta phi turns out to be this, which is a common eigenstate of L square Lz of this form YLM. Now we plug everything back, and we isolated the R part, and R part becomes effectively like a 1D Schrodinger equation problem, but not just 1D, 1D in a half line, because R goes from 0 to infinity, not minus infinity to plus infinity. So everything else is like 1D. This is like a kinetic term, this is a potential. The potential has a extra 1 by R square, which is always there, irrespective of whatever potential you are using. And that's all we have to deal with, right? That is the whole problem. So that is what we'll solve. And we have learned how to solve this kind of problem. It becomes the same story, like bound state, scattering state, all those things, exactly same. Okay. Okay, if there is no question, that's where we stop, and we'll meet again on Wednesday.